Many years ago, Sir David Attenborough produced a very popular BBC quiz show entitled Animal, Vegetable, Mineral, where a panel of experts were asked to identify interesting objects from around the world. If the word perovskite had come up, there would have been a great deal of head-scratching. But as I've learned recently, perovskite is a mineral, first discovered in the Ural Mountains in 1839 and named after the Russian mineralogist Perovsky. Fast forward to 2010, and in the research laboratories of Oxford University, a startling application was being unearthed by Professor Henry Snaith and team. 13 years on, this Oxford University spin-out, called Oxford PV, is challenging and reshaping the world of solar, making it increasingly affordable and mainstream. So today we're going to discuss why Oxford PV is transforming the renewables landscape through its development of a low-cost, highly efficient solar photovoltaic technology. And to do this, I want to welcome three guests from Oxford PV. Professor Henry Snaith, co-founder and chief scientific officer, Dr. Chris Case, chief technology officer, and David Ward, chief executive. And my job today is to discuss with you why this is so groundbreaking and probe why it might be such a compelling investment opportunity. And a big thanks to George Robinson, founder of Oxford Investment Consultants and an important backer of the company, for making this conversation possible. Professor Henry Snaith, you are the Binks Professor of Renewable Energy in the Physics Department of the Oxford University and Fellow of the Royal Society specializing in solar energy research. Welcome. Please give us a little historic perspective. Where and when did perovskite appear and how did it first start being applied?
Thank you very much, Simon. It's a pleasure to be here. Perovskite, as you correctly identified, is calcium titanate, and it's a mineral, and it was around for quite a long time, since the 1800s. But actually, the materials that we found work very, very well as solar cells, solar absorber materials, are based on tin or lead halide perovskites. These compounds were actually investigated for their semiconducting properties in the late 90s, early 2000s, but then forgotten about for another 10 years or so. And in fact, they were tested as a material to absorb sunlight and generate some electricity by a group in Japan first. They took these perovskite materials based on lead halides and organic components, what we call a hybrid semiconductor, and found they could absorb some sunlight and generate some charge from those materials. We started looking at these materials, inspired by the work from the Japanese group. In fact, collaborated a little bit with them to understand how to make the materials. And then we made some key discoveries in my university lab. And these discoveries were based around the fact that we could take these perovskite semiconductor compounds, process these materials into thin films, and sandwich them between two electrodes in a very simple solar cell device structure. And they worked incredibly efficiently, unexpectedly efficiently. And this then led to a whole load of excitement in the research communities, thousands of people around the world working on this material to try to understand its properties and drive the application in solar. And of course, we filed a lot of patents early on with those compounds and licensed those patents to Oxford PV, which was the startup company I co-founded in 2010. And since then, the company has been putting all effort into industrializing this material in a very efficient solar technology.
Henry, thank you for that. Just begs the question of, as this was being shared with the community, why weren't more people jumping on it? Or were they, but you just had a head start?
It was often a fair amount of serendipity in discoveries. This was just one material that looked like it might be interesting for solar out of a whole range of materials. We were, at the time in my research group, looking at a lot of different materials. We weren't focused on one specific type of compound. We were looking at organic materials, dyes, semiconducting polymers, inorganic nanocrystals, and quantum dots. We cast the net quite broadly. This was just one material which looked like it might have some interest. I didn't actually think it would be very good. And we put effort in and made these discoveries, some of them which were slightly accidental, about how it works so well, the structures of devices we made. And from that point, we just pushed very, very hard to drive all our efforts in my research group. I had a reasonably small research group in the university, at the time only about 8 people. We had about 12 months to really advance the core technology before we published anything, before anyone knew anything about it. And in that time, we made a lot of core discoveries, which really form the backbone of our intellectual property in the company now. Since then, yes, thousands of people have jumped on it, and we're certainly seeing more and more industrial activity as well. We're fortunate that we had the first step, the first move, which gave us these priority filings of the IP, but also gave us the head start in terms of technologically driving this material and this technology forward.
And for those of us who aren't of a scientific persuasion or even of technical persuasion, how did you think about the arrangement of the perovskite with the existing universe of solar panels?
There's 2 aspects about perovskites that lead us to doing what we're doing in Oxford PV at the moment. One is that we can change the composition of these materials. They're made of 3 components, and we can tune the ratio of these components, or we can substitute some of the components for different ions in the periodic table. And I don't want to get too technical, but in doing so, we actually change what we call the band gap, or we change the color of the material. We change the region of solar light that they absorb. So we can tune the band of solar energy that we absorb in these semiconductors. That's one aspect that's unique to perovskites over silicon. Silicon is just silicon, Si, it's single element. It makes one material and you can't tune it. That's it. You get what you're given. The other aspect is we get very, very high voltages generated from these perovskite materials, much higher than you get from silicon. So this combination of being able to generate a very high voltage, electrical voltage is part of the electrical power conversion that you need to generate energy, and the tunability of the materials mean that instead of just taking a single semiconductor and putting it out in a solar cell as a sunlight, we can stack them on top of each other in a so-called multi-junction or tandem device architecture. And that gives the ability to fundamentally deliver higher efficiency. We can convert more of the solar energy into electrical power through this multi-junction approach. And there's never been a material that's easy and cheap to process that can do this before.
That's a really good time to move to Chris Case, the Chief Technology Officer. Just by way of background, you had 10 years as Chief Technology and Scientific Officer with BOC, which is part of the Linda Group, where I believe you oversaw the global technology strategy and R&D for that $8 billion business. Chris, you've got a background in energy transition and related challenges. We start high level. What do we need to understand about the power of the sun?
Thanks, Simon, for that. I remember reading, of course, and not hearing, but Thomas Edison said back in 1931, I'd put my money on the sun and solar energy. What a source of power. I hope we don't have to wait until oil and coal run out before we tackle it. So he certainly was visionary that way. But the sun beams 470 exajoules, it's 10 to the 18th, by the way, of energy to the Earth every 88 minutes. That's equaling the amount of energy human beings use in a year. So looked at another way, the solar energy reaching the Earth is about 10,000 times greater than the rate at which we use the energy. It's now about 20 trillion kilowatt hours of energy annually. But despite having this really attractive amount of energy source from the sun, solar and solar panels only generate about 3% of the current energy mix. And that's primarily until recently because it's been too expensive to capture and distribute it. But with this perovskite and in general, for solar, it's no longer the case. Sometimes I like to use the phrase that you've heard, this concept of peak oil. And whether or not it's happened or still in the future, you'll never hear the phrase peak sun because the sun isn't scheduled to run out for another 5 billion years. So it's the ideal energy source to decarbonize. And of course, the world needs to move away from all fossil fuel-based systems if we're going to achieve any of our targets associated with the energy transition and net zero.
So the problem with many industrial developments, and I'm looking now at solar, is there's a certain amount of stasis because they get embedded across practices, and a disruptor may have a superior technology or a different approach, but there's a reluctance to adopt. So maybe tell us how it is going to have the potential to transform the industry?
It's a good question. But first, we must agree that the energy transition is required. We've got to replace this 28 terawatts per year of energy by 2050 with something else that's sustainable if we're going to meet our targets of net zero. So that's 70 terawatts of production. This is just a lot of stuff. But you've got an industry that, as you said, likes basically to be reassured of their investment and their return. Sometimes I make a comment that the people who invest in solar actually don't care what the technology is. Those fields of solar panels that you see could actually be an array of hamsters spinning little miniature turbines. All they care about is a guaranteed return on investment over some horizon, 10 or 15 years. And these technologies that in solar cells in general are expected to last more than 20 or even 30 years. So these are companies that are fairly risk averse. So introducing any new technology into a mix with investors that are risk averse is challenging. And that's why we chose this approach to introduce a technology, this perovskite material that Henry described, in cooperation or in cooperation with the existing technology with this silicon. And sometimes I use this phrase, we have a disruptive technology, that's the perovskite, but we're not disrupting the industry because we're piggybacking on this silicon material, which today still represents 95% of the traditional solar panels that are installed.
That's clear. The other issue we know about breakthroughs is it can look fantastic in the lab, but the whole journey of commercialization is a whole lot more difficult. Tell us about how you have managed as a team and now as a company this journey so far.
First of all, I'll tell you that in this technology field, solar, the typical innovations take more than 20 years to mature. So the solar cells that are in use today were actually designed and first developed in the early 80s. It's taken that long to bring them to fruition and the state of readiness in this concept of the technology readiness that people feel confidence because, again, they have to last a long time. So we're trying to achieve something actually in record time. In less than 10 years, we have managed to scale the technology. That means taking the small demonstration devices that Henry would have had in his laboratory and building much larger areas. So the sizes of the solar cells that you see on commercial solar panels, while also figuring out how to manufacture them cost effectively and assure customers that they will last 20 or 25 years. But in reality, it was a straightforward serial approach. We developed the technology and prove it in the small area. And then we made a bold move back in 2015 to actually buy a factory, a large demonstration area where we could put in equipment to show the world we could produce these in demonstration quantities for our customers. And that's exactly what we've done. The process and compositions and technology we developed are actually something we've demonstrated for more than 5 years. Most of the work now is on the industrialization and assuring the factories can deliver large volumes of these devices and meet our appropriate cost targets.
So I came to Oxford PV and I saw your work, firsthand, which was extremely impressive. And I think you've acquired a factory or a site from Bosch. So tell the listeners, please, how you are expanding the manufacturing base.
So back in 2015, in order to expand our ability to demonstrate and scale the process, we went on a journey to locate an existing facility that we could acquire. And this was under the standing that when you're a small company, VC-backed, investing money in bricks and mortar is never something the investors prefer. So they wanted to find an existing structure that we could convert for our purposes. And we ended up selecting a location in Germany. It was a factory previously owned by Bosch. And in fact, it was making a different kind of solar panel technology. It was over 12 1,000 square meters. So compared to our small 1,000 square meter laboratory capability that we have in the UK, it was enormous. It already had inside most of the facilities we needed to demonstrate our technology. And from that equipment set, we built up competency around scaling. And today, that location represents our first production facility for these solar cells.
So that's a nice explanation of the manufacturing competence. Let's talk about engaging with customers. How has that journey evolved?
One thing that needs to be clarified is who are the customers? Because the product that we make is the solar cell. That's the component, which is, of course, the actual heart of the solar panel. The solar panel is that rectangular thing that you see on the rooftops of homes and buildings or out in the fields. The square component inside is the solar cell. That's the thing that does the work. The rest of it is just holding the solar cell. So we make these tandem solar cells that Henry described, these very high efficiency solar cells. And we have, as a primary customer, a manufacturer of the modules, the solar modules. And so we went out, and in fact, it was an easy sell, so to speak, because silicon by itself, after close to 70 years of improvements, it was first commercialized in the form of a solar panel back in 1954, but after almost 70 years of development, it's reached a practical efficiency limit. You can't make it any more efficient as it is. You can probably make it a little bit cheaper, but you can't make it any more efficient. And efficiency is an important component of the energy transition. You want to be able to generate as much power in the available space as possible. So you can't change the silicon without doing something different. And that different approach, of course, is this concept of the multi-junction solar cell, where we add this perovskite material to the silicon. So it really is an easy sell to the customer because all the people who make solar panels are stuck with the same silicon challenge. It's reached an efficiency barrier set by physics, so unchangeable, and we are offering all of them a way to produce something much more efficient. So it's actually easy. The real challenge is reassuring those customers that the product that we're offering can meet their expectations from the perspective of cost and durability. That remains still one of our challenges. We don't have 10 years of field data to show people and reassure them it works. So we have to use other techniques to reduce the risk while they assess their technology.
Help us understand those techniques.
Commercial solar panels generally go through a step called certification. The certification uses a third party which assesses against industry standard techniques using accelerated mechanisms. So you try to simulate what would happen to a module after 10 or 20 years of field exposure, but by testing them only for several months. So these tests have been established for years. For the conventional silicon modules, we piggyback and utilize those same kinds of tests, and hopefully they will provide evidence that the technology that we have will last 20, 25, or 30 years.
So you've both very clearly explained the science and the technology and now the manufacturing, the customer base. I want to turn to David Ward, the Chief Executive, because all of what's been said and discussed is great, but running a business and growing a business and developing this immense potential obviously carries its challenges. Now, David, you've had 30 years of experience as an entrepreneur and a leader in VC, clean tech, physical sciences, technology companies. And I think I'm right in saying that prior to becoming CEO, you served for 5 years as the CEO of Adaptive Surface Technologies, which is a US-based industrial technology company spun out of Harvard University. And you also have the added benefit of a master's in material science from Oxford. Let me start high level. As CEO, how do you explain your primary objectives?
Thanks, Simon. Makes me seem quite old. I'll have to check in on that. The primary objective is don't mess up a good thing. We've got 13 years of fantastic progress within the business, and immensely talented group of people, both in the UK and Germany, who are executing on this plan. And I think the challenges are the ones that Chris and Henry have identified. It's interesting. It's not a technology scaling challenge. That's often the phase you find a company like this in. Can we make in large industrial scale what we can make in small scale? That's proven. It is the physical engineering of funding, building a larger factory, getting the machinery in, getting it established and getting it in a production-ready state alongside getting the long-term data that Chris was talking about. Because on the market side, over the last 2 years, it's become clear there is more demand than there is capability in the solar industry to deliver. It's very much an internal challenge around scaling up physically.
Before we get into some of those weeds, just tell me how the world of solar has changed in the last few years, because we've had the energy transition and we've had geopolitical turbulence.
To me, there's 3 elements, all of which have come together to really provide huge tailwinds for solar. Clearly, originally, there has been for a long time the environmental impact of moving to renewables, and people have seen that and supported that for a long time. That was clearly magnified during COVID. You've seen a lot of more environmental focus coming out of that period. So that just reinforced an existing thread of support. The one that's definitely changed and enhanced is energy security. With the invasion of Ukraine and the instability that gave to energy supply within Europe specifically, and a tangent, the US positioning versus Chinese supply of basically anything technology, that has now meant there's a political argument to do renewables based on energy security, which puts you at a very different end of the political spectrum to those worrying about environment. And then finally, there's pure cost. Solar will be the lowest cost of energy generation, and so therefore everybody wants that, cheap energy. Those 3 strands are the ones that have really put PV in a different place to it was 3 years ago.
And at the same time, what's happened, or how would you assess the competitive landscape?
It's in 2 parts. There's existing technologies that Chris and Henry were talking about in silicon and other materials, and they're basically just running flat out in order to meet market demand that is beyond them today and is going to be increasingly beyond them as that requirement moves forward. On the perovskite specific side, again, as spoken to, we have seen many thousands of people now working in perovskites, but Oxford PV still has a lead for sure in terms of the development of this materials. It has a very strong position in intellectual property, which makes it quite hard for people to come and do exactly what we do. And so therefore, I feel that for the rollout of perovskites within PV, Oxford PV is in an excellent place. There'll be other players as well. It's not a one player takes all type industry given the scale of it. We're positioned really well.
The other force in the background that we don't see as obviously is the impact of government policies. And of course, they will influence the arrangement of the chessboard, won't they?
Completely. In both the US and Europe, there has been policy changes and policies put in place that will fundamentally support the economics of moving to renewables. The US is a really interesting place from that point of view. They got burnt by the last wave of solar in terms of public funding going into solar, Solyndra being the example that's always quoted as something that bugged the Obama administration for many years post. But then suddenly, once you get this change to, no, we need to do this, the US moved from nowhere to somewhere very quickly with the Inflation Reduction Act they have in place. Europe is playing catch up a bit with that. But it will absolutely influence where people are putting the next wave of solar facilities, whether that's cell production, whether that's module production. And the same is true for us. Coming to you here from Boston in Massachusetts, we have a factory already in Brandenburg, Germany. So we're in the right geographies, and we're clearly having those conversations with governments in terms of support.
So let's just stay with that map of production and client acquisition, and then we can talk about finances. As we look out over the next few years, how do you see the roadmap?
It's very much a case of building scale. Gigafabs is the name du jour of large factories in multiple new technology areas, but it's practically true for us. People are putting in now gigawatt plus production size facilities, and I think that's our roadmap. Where do we put the first gigafactory? Because there will be more than one, but where do we put it? and the timeline to fund and to procure the equipment for that. But that's the scale you want to operate at. Primarily, that will be a cell factory for the tandem cells, although the end product is modules, as Chris explained a little earlier in the conversation. We could do modularization, but mostly there's a bunch of existing companies that do that and are the connection to the end customer base as well. That's our focus, is build gigascale cell production factory.
So the two financial aspects that are absolutely key are the trajectory of revenues and profitability and financing. So can we start with how you foresee revenue growth?
It is a straightforward function of our output in the sense that the initial cells that come off our line go into the certification process, go into demonstration customers, are going into us seeding the market with initial product. Once you're through that period of confidence and comfort from the marketplace, then in effect, we're just providing our cells to the module makers on a third-party supplier basis. They put their brand on the product, on the modules, and sell it to their customers. Then we're in the normal supply chain. So what I'd regard as real revenue, which is the cells sold commercially on a third-party basis, is a phase that will come probably in 2020, early 2024. That's not to say we're not getting some income in the meantime, but it's being really fierce about really counting what revenue is. That's the 24 number. And then the pathway to profitability for a business like this is scale. It's just a function of scale. So that will be during the gigaphase factory time.
The financing to date, you've had a variety of sources of finance. How do you envisage the financing evolve?
We've been very grateful for the variety of investors we've had in the business through the last decade plus. The landscape has changed a bit, again, because of these tailwinds for solar. There are some much larger investors, private equity or large family offices, or even some of the sovereign funds that are looking to deploy large amounts of money into renewables for the future. I do see that as a positive thing for us. When you can grow to a certain point, debt becomes a reality. But I think the landscape at the moment is equity, and there are players around who can write $100 million, whatever currency you like, check into a business like ours, given the pathway forward. So not going to talk about specific fundraising quanta for us on this conversation, but what you see is the ability to raise substantial sums of money through equity in the market right now.
And we have been conducting a series of conversations on the Money Mates podcast with the sovereign wealth funds, and I would say that's absolutely echoed with their indications and their appetite to be able to commit important amounts of capital to this area. Could we just go upwards to the board? Absolutely key in the evolution of companies is board composition and board influence, so they aren't just rubber stamping the page. Tell us a little bit about how you thought about building out a world-class board.
A very quick bit of history in the sense that I was on it for many years of Oxford PV as representing one of the earliest investors in the company. I'm now rather quickly in the other side of the table, so that may colour my views a bit. But I think we've had a really good mix of experienced early and growth stage investors who have seen many of the trials and tribulations of companies like ours in the first 5 or 10 years of its life. The challenges are the same. It doesn't really matter what sector you're in. It's all the growth pains are very similar. So that's been great. We've now got large institutional investors with people like Equinor and Legal & General on the board to, again, bring a whole new perspective to both the financing, but also the customer and use side, because both of those are connected into the end markets as well. And then the third element is really solar-specific knowledge that we can add to even that which is in our executive team. But outside of that, we've had a number of solar experts in the marketplace on the board as well. We're pretty well served. I'm very fortunate to have that group. It also covers a bunch of different constituencies that can help. It's definitely an active board. It's definitely not a rubber stamping one. We had a call several hours ago with a regular update where we get guidance and input from them. It's been a good process, and I'm happy to be on both sides of it.
That reminds me, we had Nigel Wilson, CEO of Legal & General, on the podcast, and he was talking about, again, one of these being the key areas that they highlighted. I didn't ask you when we talked about the path to profitability, but as you think out, are you thinking about the margins of a business like this, or the returns on invested capital? Again, looking out, how should we think about it?
At scale, there's a really clear margin driver. If you look at current utility prices, future utility prices, and the inherent costs of what we do. The perovskite materials themselves are not expensive. The silicon-based cell that we're using right now has been, as Chris has said, evolved over 70 years to also be very cheap. So there are no inherently expensive steps in what we do. And there's a clear and pretty straightforward business model that shows a path to profitability based on volume. And that statement is basically true for the utility marketplace, so in many ways the most challenging from a price perspective. But there's also a really large and growing sector of specialty products on confined areas, whether that's from rooftops or even down to other areas such as automotive or space or a bunch of different applications where solar becomes an energy generator of choice. And their sales prices are higher, and therefore margin and the ability to tailor more specific products is there. I think we've got two parts of the business. The underlying one is the volume one in utility scale, which is inherently a profitable business at scale. And then there's specialty products, which are lower volumes, but probably higher margin.
I want to bring Henry and Chris back in because I want to just talk about the environmental question, which is part of the larger ESG debate. We know why solar is absolutely key to solving this equation, but there are manufacturing processes and there are byproducts. Henry, start with you, the person who's envisioned and worked on this. How have you thought about this as you've gone along?
Certainly, sustainability and the ecological impact of solar is really important to consider. Solar per se, we have to transition to 100% renewable energy. This is almost fact. People almost take this on board. Although surprisingly, there's still many predictions that still have a certain level of fossil fuel production in 2050. That is just not going to be acceptable. And it won't happen because the cost advantage of solar is going to dominate. In terms of the renewable energy technologies themselves, there is energy required to make them. There's factories needed to be built. There's materials needed to be sourced. We have to consider these things. We've done a number of life cycle assessments of solar, of the perovskite and perovskite on silicon solar technologies. And there, what's really apparent is actually the embodied energy and the environmental impact of the silicon wafer is the main driver for the environmental cost of solar today. And that's because there is a lot of energy needs to be put into producing the silicon. And unfortunately, most of that energy or the electricity used is presently used from coal-fired power stations. So as the grid converts to renewables and the silicon's produced in places where the electricity is produced from renewables, then that will become greener. But today it's predominantly coal-fired power stations. So there is a carbon impact. The payback or the carbon payback compared to fossil fuel power production is still less than a year. So you're getting 24 plus years of free electricity in terms of carbon versus the 1 year you cost to make it. But we can do a lot better than that. The perovskite adds, because it's a thinner film, there's about, in terms of thickness, 1 micrometer of perovskite layer compared to around 150 micrometers of silicon, so much less material. It doesn't require high temperatures. Silicon needs to be annealed, cured at 1,800 degrees to melt it. Perovskite doesn't need to go hotter than 150 degrees, so much less energy input into the material. And the overall assessments put the energy payback on the order of a few months rather than years. So there'll be a big saving on the perovskite side if we could move entirely to the perovskite. That's the longer term vision. In the near term, every extra percent efficiency or every extra watt we can produce out of that silicon wafer by putting the less costly to process perovskite on brings that payback time shorter. If we could double the power of that wafer, then the payback is half the time in simplistic terms. So the benefit to improving the environmental impact of solar, of perovskites, is very much about reducing the amount of energy that needs to go into producing a kilowatt hour of solar.
Thank you. Chris, you've got lots of experience in this whole area. How do you reflect on this?
One of the things we actually did as a company is to look at these considerations of sustainability and circularity more than 5 years ago. So we're still a relatively small company, but we did not want to get caught out in the paradigm that we were promoting a technology, developing a technology, and then discovering that the availability of the critical raw materials would constrain our ultimate growth. You can see just in the world of batteries, all the debate about the sourcing and availability of the cobalts and nickels that go into the batteries of modern vehicles for storage and in the electric vehicle transition. So we actually critically looked at the availability of the raw materials. The materials that go into perovskite are relatively inexpensive, and fortunately, they're broadly available. So you can find them as what's called primary mine source. That means if you need more, you just dig up more from the world. And they're available in regions that have no conflict. And by conflict, I'm generally referring to the idea of forced labor, which goes into consideration in the production of many of these other critical raw materials that go into the production of solar panels from the East, and of course also in the raw materials that go into batteries and storage systems also. And as I said, the nice thing is the perovskite materials are broadly available. In fact, there is enough raw materials to sustain more than 30 terawatts of perovskite production. That easily takes us into the time frame of 2050 or beyond in terms of producing things. And that means really having an annual production of 3 to 4 terawatts per annum of PV sometime in the next few years to start to reach that net zero target. Echoing what David Ward said is this is a huge business opportunity. I sometimes make this comment about sustainability. We're in the business of developing a sustainable technology, but to be a sustainable business, you actually have to have a sustainable business model. So we're not in the concept of just doing something that is not representing a good and sustainable and profitable business. And I think it's critical that we really target these net zero goals that have been announced variably between Europe and the US and the East.
So, in assessing what's been said, two things strike me, and I'm going to just come back so you can clarify them. And I might start with this question with Chris. I think non-scientific investors and listeners will have understood why this might be the most significant invention within renewable energy. And yet, is it clear? And if it isn't, maybe you could tease it out why and what is the benefit of this high energy intensity and why it's so valuable as opposed to just making more of the existing panels.
Great point, Simon. Cost reductions in PV, photovoltaics, have been driven by three factors: efficiency improvements, manufacturing productivity enhancements, and reduced materials costs. Let me remind you of a not so obvious fact. In reality, the cost of the photovoltaic solar cell is only about 15% of the cost of a system. A system means the solar panel, the battery, the inverter, the installation costs. So reducing the cost of that cell by, let's say, 20% has only a small, maybe 3% impact on reducing the cost of the energy that's generated by that system. Whereas if you raise the efficiency of the solar cell by 20%, it has a nearly direct reduction on the cost of energy produced. And of course, ultimately, it is the cost of the energy that's produced that counts. It's not the cost of producing the solar panel, the cost per watt. It's the cost of that kilowatt hour of energy that you really want to assess when you're comparing technologies. And of course, that's the problem, that the multi-junction approaches are the perfect solution. You could say, well, how much space does PV need? Well, they've done lots of these calculations, and you could achieve net zero, in other words, 100% PV, if you filled an area roughly the size of the state of Texas with solar panels. And in reality, being able to deliver more power per unit area is important. There is just a finite number of attractive spaces. If you're in a city, you've only got the rooftops of the buildings in the cities. If you're in a very highly densely populated area like Japan, you have very small rooftops that you can cover with solar. So having the ability to produce more power in that limited area is important. And even in applications like utilities, where you're developing large fields, as much as a gigawatt or more installations, there's still only finite numbers of areas that you can deliver those things and make it easy. So high power density is a critical part of the perovskite multi-junction solution, and in fact is the only credible and demonstrated ability to do that in the near term. And I think it's an important part of the value proposition of our technology.
David, I just want to come back because as you build out this manufacturing capability, for a long time, the Chinese particularly had arrived with the large-scale industrial processes and applications and perhaps labor cost advantages. And am I right in saying that it's the arrival of the perovskite solution that is giving the technological edge that is allowing you to more than equalize, in fact, leapfrog ahead in this space?
It is around the increased efficiency. In other words, you can only reduce cost on something so far and get to almost zero. And then the improvement in efficiency, the 20% more power we can generate from the same area on our tandem cell versus a traditional solar cell, means that there is no competing with that by just reducing price. There is only one way of achieving that power improvement, and that's by doing it through the tandem that we have. So I think that fundamentally does change the game. Now, clearly, Chinese PV industry also sees this and will be working on and are working on perovskite as well. That's a fundamental shift and a reason why I think you see the amount of interest going on into perovskite, into tandem solar, into solar in general. But in more traditional Western geographies, because the next waves, the next generation of solar will not all be about how cheap can you make your cell. It will be about how efficient can you make your cell.
I have to give a last word to Professor Henry Snaith, because it all started with you on your lab bench or under your microscope. How are you feeling now, 12 years on?
Obviously, massively excited by the possibility, by the achievements we've done, but really by the possibility of where we can go. We're tiny in the potential for where we're going to grow to. Obviously, we're right on the verge of production, selling real products. And it's really how we can execute this next stage to get towards gigawatt scale and then actually to become dominant in this industry. It's about growth and it's about having those economies of scale through growing. And that's how the Chinese companies over the last 20 years have got to the dominance they have. It's through continually reinvesting in growth and taking on the new technologies and advancing. And we've got this opportunity with this perovskite to really deliver something that's much better than where everyone else is now. But then we need to run with it. We need to really push that forward. So very excited. And obviously, it's almost a fairy tale coming from the lab research to where we are. But if you ask me in 10 years' time and we've got to our 60 gigawatts production capacity and we're going to start to take a significant fraction of the global PV production and we're well on the way to a transition to 100% renewables, I'll then say, yes, this has been a fairy tale. At the moment, we're in the birth of the fairy tale. Things are looking good.
It's clear you're all very excited. I think our listeners will understand why that excitement is being generated by the work that is probably, as I said, the most significant invention within the renewable space. I should also mention that this is not the first of the Oxford University spin-outs. As I was doing my research, it was interesting to note that in 2021, a study was done that crowned Oxford University as the best for successful commercial spin-outs measured over 2 decades. The numbers were that Oxford University spin-outs have raised a total of £3 billion in funding, but are now worth over 8. So you're part of that ecosystem, and George Robinson is obviously very involved in that, as I mentioned earlier on. Incredibly exciting what is being done here in and around Oxford. Thank you very much, gentlemen, for your time today and for explaining what is such an exciting story.